Hello, my name is Gosia Konwerska. I work as a developer at Wolfram Research, and I'm gonna be talking about Poisson.
This is also not really a talk about the spatial point data analysis. There'll be some maybe spatial point data, but mainly I'm going to talk about Poisson, and not the fish, but the person, as we try to establish. And so some background. So why really look at the Poisson? And one reason is because I actually worked recently a lot with Poisson, but also we have a lot of namesakes in Wolfram language. So if you look at all the names that would contain Poisson, that's quite a list. And I have 12. Probably your version of Mathematica has 11, but we'll get to that. And when you connect to the outside world like Wikipedia, then you can see that actually there's so many more things that were named after that person in physics and also in mathematics and whatnot. And so we can ask our entity framework to who this person was and did he had any notable film appearances and whatnot. And this is Poisson. He unfortunately died before the golden Hollywood era, but he was a mathematician, and I would say he was quite a prolific one. We don't have here really his major accomplishments, but if you can look at the number of things named after him, it's worth exploring some of the features. So I'm going to start with the basic one and the most known one, which is the Poisson distribution, and that was actually derived by another French mathematician, de Moivre, but was popularized by Poisson, who was using it in a wrong way to prove something wrong, and in like century later. So we have a Poisson distribution, that's our symbol, and it is defined with one parameter, usually denoted mu, and this has to be positive real, and this is the mean of this distribution. So this gives us the likelihood of a given number of independent events that happen in some fixed interval at the known average rate. And so that was originally used, looking at the deaths of soldiers in the army by being kicked by the horse. We don't really do this now, but we have lots of things to model with. So the internet traffic, the phone call arrivals, any arrivals actually, scorings at the sporting events and such. So this tells you kind of what it is, represents the Poisson distribution with mean. And so when you look at the properties here, the mean and variance, you see that they're the same. So the problem kind of here is to keep in mind that if you increase the rate, the mean, so the kind of the rate, you also increase the variance of the distribution. But can model independent events, and so what I would like to kind of work with. So let's see if we can model accidents in Champagne. And the rate here, it's completely fake. Okay, I have no idea how many accidents are in town. So please bear with me that it's just illustratory example. We can sample from this distribution using the random variate. I am not printing all of those 365 events, but we can plot it using, for example, list plot, and the orange line is the rate. So they oscillate, the number of events oscillate around the mean. What is nice about the Poisson distribution is that if you have two random variables that are independent and both Poisson distributed, their sum is also Poisson distributed, and the mean is the sum of the means of each of those. So now if I take the accidents in Urbana, the twin city of Champagne, and then I want to find out what's the sum of all the accidents in our two cities, I can model this by another Poisson with the new parameter. And so we can simulate that, plot, compare. So the simulation was from the new distribution, but what I can do also is to simulate independently the data for, from both distributions of both cities, and then use estimated distribution to fit the new Poisson into this, the sum of these two data. Out of curiosity, the difference of two Poisson distributions has its own symbol in Wolfram language. It's a scalar distribution. The mean is the difference of the means, and the variance is the sum of the variances. So if I want to look at the difference of the accidents between the Champagne and Urbana, this is more or less what it might look like. You can't see, but now you can see. Okay. So Poisson distribution, we just have a bunch of events happening, and we don't worry about their, timing. If you want to worry about, how they happen in time, meaning that I'm looking at, say, arrivals to somewhere, that means that I'm looking at those in their order in time, and we have another model, which is the Poisson process. And in Poisson process, we model the counts of independent events that are ordered in time. So I define the Poisson process. What is nice that for the Murphy folks, that this is a process that has independent increments. So basically, what happens now doesn't really depend on the past. So the Poisson process gets its name because the slice distribution for each time is actually a Poisson distribution that depends on the parameter of the process and also on the time at which we take the slice. So now, if we would go back to our accidents and would like to now model these accidents in hours, knowing the daily rate, so I define the rate per hour and define the new process, then I can simulate possible count, say for 2 days, so up to 48 hours, using random function. And the result of this is a temporal data, and this is more or less what it can look like in a simulation. If I have right now created data that has many paths, just 1,000 paths, then we can look at the slice distributions. So this is many paths. So after 24 hours, a slice, it's going to be some distribution at this point. This is a slice through the data, through the path, many paths of the processes, and the object here is a data distribution. There are some properties of this data distribution, and for us, the important is the domain, which would extract the data. So I can compare the PDFs from the simulation and the process slice distribution. We can compute the mean, and this is the slice, the data. And then we can take this slice and then feed the Poisson distribution into this data. But because we know what it is, we can also figure out by analytically what's the distribution. It's not the best estimation. This is maybe not the biggest sample. Also, the times in this Poisson process are assumed to be coming from exponential distribution. They're assumed to be independent. So if I take the original data, which is our here simulation for Champagne, and I take the times, that's just from a single path. Okay, then I can estimate the exponential distribution, but we also know exactly what's the model for this distribution of the what's called arrival times in this way. So that was a process that had a constant rate. Okay, we have an extension of the Poisson process in Wolfram language that allows you to specify your custom varying rate, which is going to be varying in time. And this is in homogeneous Poisson process. And since I was talking about accidents, the next logical step is actually going to emergency room. So what I want to show you is an example when we have a time series of number of patients arriving to emergency room per hour in a 24-hour cycle. So this is the arrivals. This is how it looks like on the plot. And I think that actually better visualization is to hack a bit the sector chart and to see that, people going for lunch, around lunch hour, we'll get into some trouble, and then people leaving work will cause some troubles, and then when people sleep, actually, we don't have many patients at the emergency room. So that seems logical and plausible, average rate for such event. So what I'm going to do here is to define the rate function for my homogeneous Poisson process using interpolation, and then define the model putting in this interpolating function defined from the time series. We can then simulate and kind of see the black dots are that's going to be the original accumulated data, and all this kind of thin lines are our simulations for this process. We can then work with this model. So maybe you can ask what's the probability, the number of patients arriving between 2 a.m. 3 a.m. is at least 10, right? So not so much. We can also ask what's the expected number of patients arriving by 6 a.m. 32 people, right? So that's going to be from midnight in this model. So see that the slice, I'm using here the slice, and then I can work the probabilities and expectations like with any distribution. Okay. The next object, kind of Poisson object in Wolfram language I would like to present is the compound Poisson objects. And in this model, basically, we start with the process, and then we're going to derive the distribution from this. So compound Poisson process, it's another extension to Poisson process, but in a different way. We are having kind of the same arrivals with the same rate, but what we are accumulating are actually independent jumps from any distribution. So before in a Poisson process we were counting, so we were kind of accumulating once. And in this case, the jumps might have actually any value that might be a random variable coming from any, say, univariate distribution. So this is an example, and how does this might look like. So I have a compound Poisson process with rate 10, the arrival rate. So the jumps, happen with the times of exponential distribution with parameter 10, and then the jump size is the normally distributed, and here the mean 0 and standard deviation 1. If I put Bernoulli distribution of parameter 1, we get the equivalent to the Poisson process itself. They have the same slice distributions. And an example for such a use. So, for example, we are having a online purchase system that the prices that we add of items that we add to the online basket follows a viable distribution, and we cannot finalize the order until it exceeds $50. And this is my my model compound Poisson process with quantity distribution in dollars, but really this is a viable distribution. So I have a quantities distributed according to viable distribution. Let's define that, simulate, and see how this looks like. So the black line here is the mean, maybe not now, and the orange one is the $50 kind of our limit. So we want to kind of see where we stand after the 2 weeks. So that's the mean value of the simulation after the 14 days. So now, because we are often interested in what's the distribution of the slice from this process, we have the compound Poisson distribution that describes exactly the distribution of the slice for the single time. So after 11 days, say, that's going to be again the quantity distribution, because I defined as jumps actually using dollars of the compound Poisson distribution with all this information inside. So the rate and then the distribution. So I can again simulate here, And then we can compare the means. So you can see that the first mean is of the distribution. So we know, the distribution. Second is the simulation from the distribution. And the last one is actually the simulation from the process. And so this is the slice of the process. So unfortunately, there is no closed form for analytic formula for the PDF, but because we can simulate, we can kind of see what's the shape. And then we can again compute numerically some probabilities. So that's going to be probability that we finalize an order within 11 days. That's less than 1/2. Or we can have a probability of finalizing the order within 20 days, which is more likely. So okay. So why I'm kind of obsessed with Poisson a little bit is because one of the things that we are looking at is the spatial process, the spatial data, and one of the major objects and models in this theory is the Poisson point process. And so this is an example of the spatial process that's going to model uniformly and independently distributed locations in space. And that means that any two disjoint regions, the number of points, if I simulate this over some region and I take two subregions, the number of points in any of the subregions is a random variable, and they're both independent. And each of these variables actually it's as a Poisson distribution. So this is our model, and it's going to depend on two parameters: mu, which is the intensity, and then dimension in which we are. So, for example, the two-dimensional process, it could be with intensity 40, and then 2 is our dimension. The intensity, it's gonna kind of tell you how many points you're gonna end up, because the thing is that when we're looking at this process, we don't really know how many points we have in any region a priori, right? It's this intensity that governs how many how many points are. Yeah, there will, yes. And so if I define, say, some region, so for simplicity, just a rectangle, which is actually a square, I want to simulate the number of points in this space. I'm gonna have well, again, new object and new simulating function, and also new container for the data. So this is our spatial point data that was really a bit too shy to come and be its own star of its own talk. But this is a little preview that we are kind of working towards the spatial, data analysis and spatial data models. And so, despite the same intensity, if I simulate this again, I will get. You kind of see here data points in this blob. The first information is a data point. So if I evaluate this again, this number of points will change. And so the number of points in this whole region is governed by the Poisson distribution. So, so then the pattern basically also changes with each simulation. So there will be some properties of the spatial point data that I will not elaborate on the total of them, but one of them is we would like to know the point count, so we can actually extract this from the data. We can, like in a standard temporal processes, we could have multiple paths. In this way, we can also have multiple configurations for the spatial points. So this is the 1,000 configurations. This is a new thing coming here for all our kind of blobs, that if the data is too large, it may not be automatically saved to the notebook, but you can store it by just one click. Okay? And that would also happen if people use temporal data, just a heads up. So here, what I have, I extract the point count, but because I had so many realizations of these patterns, that actually gonna have, it's gonna be a list of length 1,000. So for each of these realizations, and you can see, first 5, they're gonna be around these values. But what is more interesting is then we can actually analyze the histogram and then analyze the distribution. And as I said, this is governed by the Poisson distribution. So you want to fit a Poisson distribution into this sizes, so this point counts. What we can do is to test the goodness of fit using distribution fit test. And I would like to point out that the significance level is 1,000. And I did this because I know what Eduardo is going to talk in the near future about p-values and the significance level. And we should use a much lower significance level to improve our tests. So that's the comparison with the PDF. This is from the PDF of the estimated model. We can also do this for a different region, right? So this random point configuration takes a region, right? So here I would like to do this on a unit disk, and then estimate again the Poisson distribution. Test the goodness of fit for this, and so question is what's the formula? So if what we can do here, this is a theoretical analytical approach. New symbol again, point count distribution applied to a spatial process, okay, and applied to a region. I would like to know what's the distribution of the number of points from this process on this region. So that gives us a Poisson distribution 4 times mu, okay. The region measure for our region, which was the rectangle, it's 4. And so that kind of gives away a bit what's the formula. If I have a disk, it's the Poisson distribution with pi times mu. The region measure, it's pi. So basically, the formula depends on the distribution of the point count is the Poisson distribution when the mean is the mu times the measure of the region. Here, the other claim that I made at the beginning of this model was that the counts of points in 2 different disjoint regions are independent. And so we can also try to ascertain this via sampling and some example. So I create 2 subregions of my original rectangle, and then I sample. So I have a sample one which takes the point count. So this is the same property, but then I give a second argument, which just means, okay, give me the point count of this data only over this region. And then we can test if these samples are independent using the independence test. And the test conclusion, not rejected, so that's a good sign. And we can also compute this analytically from the model. So because our regions were disjoint, we end up with a product distribution in which we assume that in this product distribution that all the components coming in a product distribution are independent distributions. They describe independent variables. So this is where it gets us. Thank you. And if there are any questions, I have time to answer.